So in exercise 5, we're asked to determine the equation of motion for a simple pendulum. So here I've drawn a diagram. We have a mass m on a string of length L at an angle theta to the normal. As the mass swings, its height changes, given by this height here, h, and therefore this distance here is going to be L, the length of the string. So first of all, you should have taken the route of using the Lagrangian and the Euler-Lagrange equations to figure out the equation of motion. So when we do that, we first of all say the Lagrangian is equal to your kinetic energy minus your potential energy, which I call U. So that's easy. We get a half mv squared is equal to m over 2 multiplied by L theta dot all squared. So I came about this, if you think the arc length is equal to r times theta, in other words L times theta, so this distance here is L theta. So therefore the velocity of the mass going through this distance L theta is L theta dot. You just differentiate your position, okay? So therefore it's going to be L theta dot squared. You differentiate your arc length. So that's our kinetic energy, and our potential energy, U, is going to equal mgh, where h is this height here. Okay, so overall our Lagrangian is going to equal m over 2 multiplied by L theta dot all squared minus mgh. Okay, so what is h? We need to get in terms of L and theta. So I'll quickly show you what mgh is. So when we carry out the formulas for h, we get m over 2 L theta dot squared, well, like we have as the kinetic energy, that doesn't change, and we get minus mg L minus L cosine theta. Okay, so if we want to find h, we sort of need to find this distance here. So let's use our cosine. Our cosine is equal to our adjacent divided by hypotenuse. Our adjacent is going to be this angle here. Our hypotenuse is going to be L. So we get the cosine of theta is going to equal our adjacent divided by our hypotenuse, x over L. So this distance here is going to be x. Therefore, we get x is equal to L cosine theta. But we want to find h, so therefore we do our L, which is this whole distance here, minus this distance here, is going to give us this distance here, which is h, okay? So therefore we get h is equal to L minus L cosine theta, okay? And therefore mgh is going to become mg, factor out, mg L minus L cosine theta. So we can factor out an L, so our Lagrangian is equal to m over 2 theta dot squared minus mg L 1 minus cosine of theta, like so. Okay, so we found a Lagrangian, that wasn't too hard, but we need to find the equations of motion. So the equation of motion is given by the Euler-Lagrange equation. The Euler-Lagrange equation, you might have memorized by now, is the partial of L with respect to theta, which is our variable in this case, minus the rate of change of the partial of L by r theta dot, and this is equal to 0. Okay? So we need to now use this equation for our original. I'll just write it down again. We had L is equal to m over 2 L theta dot squared minus mg L1 minus cosine of theta. Okay? So let's first do dl by d theta. So this side of the equation here, m over 2 L theta dot squared, or kinetic energy, that's going to be treated as a constant. Theta dot is not theta, so that, when we differentiate, goes away. So we just need to focus on this here, mgl 1 minus cosine theta. So when we factor this here, we get mgl minus mgl cosine theta. So we need to differentiate this with respect to theta. That mgl is a constant, that goes away. So we're left with mgl cosine theta. Differentiate that, and we're going to get minus mgl sine theta. Yeah, differentiate cosine, we get minus sine theta. So dl by d theta is minus mgl sine theta. So now, the next part of the Euler-Lagrange equation, we minus the rate of change of our dl by d theta dot. So now, this side of the equation becomes a constant, because we're dealing with theta dot, so that goes away. So we need to focus on the kinetic energy. Okay? So, I may as well write this out. M over 2, expand, we get L squared theta dot squared. So we differentiate with respect to theta dot. So using the power rule, we bring this 2 down from the theta dot. Remember, m over 2 L squared is just a constant. So therefore, we're going to get m L squared over 2 multiplied by 2 theta dot. Yeah, you just bring the 2 down using the power rule for derivatives. Therefore, we're going to get m L squared divided by 2 theta dot, and that's equal to 0. Okay? So, I think we can do something better than that. We need to find the rate of change of that first. So, this, that's separate. So this is going to equal mgl sine theta plus, we're just switching the negatives and negatives to make a plus, the rate of change of, so the 2's cancel, yeah? So we get ml squared theta dot is equal to 0. So we're almost done. So what else can we do? We can cancel out the m's. So we get gl sine theta plus the rate of change of L theta dot, and that's equal to 0. So now we can differentiate L theta dot, and that's obviously going to be L theta double dot. Yeah? It's basically differentiating our angular velocity, and we get our angular acceleration multiplied by this constant. The constant doesn't change. So finally we get g sine theta plus L theta dot dot is going to equal 0. Okay, and that's L squared, of course. So yeah, differentiate L squared theta dot, we get L squared theta double dot, cancel out the L's, we're left with that. Hope that makes sense. So again, I'll say that again, we have L squared theta dot, differentiate that, we get L squared double dot, then we can cancel out those L's to give us g sine theta plus L theta double dot equals 0. So all we've done is use the Euler-Lagrange equation to find the equation of motion from our Lagrangian we had here. Okay, so that's not too hard. But we can make this look slightly better. We can say, what could we say? We could say theta double dot is going to equal g L sine theta. Okay? Just rearranging that equation. So that's saying the angular acceleration is equal to g over L sine theta, which is approximately equal to g over L multiplied by theta dot. Alright? Now, I'll quickly do this as an extra, but we know the force is equal to the rate of change of momentum. Now, I'm trusting you that you know knowledge about the Euler-Lagrange equation. So, force is equal to the rate of change of momentum. Therefore, force is going to equal dl by d theta. So if we do this quickly, we get the force is going to equal mgl sine theta. So it's basically this part that we did, and that's the force, okay, acting on the mass as it swings. Yeah, so there is the equations of motion for a simple pendulum. Okay, so well done if you got that, and I'll see you in the next video.